You have been in space for exactly 340 days. Your face looks puffy, swollen, like someone inflated it from the inside while you slept. And no, you are not sick, you are not injured, you are simply floating. For almost a year, your blood has not known which direction is down. On Earth, gravity pulls it toward your feet. Up here, it spreads evenly. It pools in your face and chest. Your legs, meanwhile, start to thin. Astronauts call them bird legs. Your body, without ever being told, begins to forget what standing up means. This is not a metaphor. This is what happened to Scott Kelly. In March of 2016, NASA astronaut Scott Kelly returned to Earth after spending 340 consecutive days aboard the International Space Station. It was the longest single spaceflight by an American astronaut in history. And when his boots finally touched solid ground, his body was not the same body that left. His identical twin brother, Mark Kelly, also an astronaut, stayed on Earth. Same DNA, same genetics, same parents, same childhood. One went to space, one did not. NASA called it the twins study, and it became the most detailed look at what long-duration spaceflight actually does to a human being. What they found should change the way you think about your own body. Let's start with the thing you would notice first. Your height. In space, without gravity compressing the discs between the bones of your spine, those discs expand. They hydrate. They swell. Scott Kelly grew approximately 2 inches during his year in orbit. He came back taller than his twin brother for the first time in his adult life. But the moment he returned to Earth, gravity started compressing those discs again. He shrank back within weeks, and his back hurt the entire time. The taller you grow in space, the more painful your return. Now let's go deeper, much deeper. Your bones are alive. You probably know that. What you might not know is that your bones are constantly being broken down and rebuilt, even right now as you sit or stand or lie in bed. This process is called bone remodeling, and it depends on mechanical stress. When you lift something heavy, when you walk, when you climb stairs, your bones respond by adding density. They strengthen where they are needed. In space, there is almost no mechanical stress on your bones. You are floating, you are not carrying your own weight, and so your body, being the efficient machine it is, starts to break down bone without rebuilding it. Astronauts lose roughly 1 to 2% of their bone density per month in space. After a year, that is a staggering amount. It is similar to what an elderly person with severe osteoporosis might experience over several years on Earth. Scott Kelly's bone density dropped significantly. His hips, his spine, his legs, the very structures you depend on to hold you upright were slowly dissolving. And it was not just your bones. Your muscles were disappearing too. Without the constant work of fighting gravity, of holding your posture, of walking, of simply existing in a gravitational field, your muscles begin to atrophy. They shrink. Your calves, your thighs, your back muscles, the muscles that keep your spine aligned, all of them start to waste away. NASA requires astronauts to exercise roughly 2 hours every single day on the space station just to slow this process. Not stop it, slow it. Even with that exercise, Scott Kelly lost significant muscle mass. When he tried to walk after landing, his legs buckled. He needed help. After a full year of rigorous daily exercise in space, the simple act of standing was exhausting. But here is where it gets truly strange. Your eyes start to change. Roughly 60 to 70% of long-duration astronauts develop what researchers now call spaceflight-associated neuroocular syndrome, or SANS. In plain English, the fluid shift that puffs up your face also increases pressure inside your skull. That pressure pushes against your eyeballs. Over months, it can flatten the back of the eye, change the shape of the optic nerve, and blur your vision. Scott Kelly reported his vision worsened during his year in space. He was not alone. Many astronauts have come home needing new prescriptions for their glasses. Some have experienced permanent changes. The longer you stay, the worse it can get. And then there is the radiation. On Earth, you are protected. The planet's magnetic field, called the magnetosphere, deflects most of the high-energy particles that stream from the sun and from distant exploding stars. You never feel it. You never see it. But that invisible shield has been saving your life every single day since you were born. The International Space Station orbits partially within that magnetic field, but not completely. Astronauts on the ISS are exposed to roughly 10 times more radiation than a person on the ground. During a full year in orbit, Scott Kelly accumulated a radiation dose that would be equivalent to roughly 50 times a normal annual background dose on Earth. Radiation damages DNA, it breaks strands, it causes mutations, it increases long-term cancer risk. NASA carefully tracks each astronaut's cumulative radiation exposure because there is a career limit. Go over it and you cannot fly again. But perhaps the most unexpected discovery from the twins' study happened at the level of your telomeres. Telomeres are tiny caps at the ends of your chromosomes. Think of them like the plastic tips on shoelaces. Every time a cell divides, those telomeres get a little shorter. They are a biological clock. As they shrink, your cells age. Shorter telomeres are associated with aging, disease, and death. During Scott Kelly's year in space, his telomeres got longer. Let that sink in. In space, his cells appeared to become biologically younger. Scientists believe this may have been related to the intense exercise regimen and dietary control on the station. But here is the twist. Within 48 hours of returning to Earth, his telomeres began shortening rapidly. They shrank below his pre-flight baseline. Some researchers suspect the rapid shortening was a stress response. His body crashing back into gravity, radiation damage catching up, cellular systems recalibrating all at once. The full picture is not that space makes you younger. It is far more complicated and far more unsettling. Your immune system also changes. Studies across multiple astronaut blood samples have shown that immune cell function shifts in microgravity. Some dormant viruses reactivate. Herpes simplex virus, varicella zoster, Epstein-Barr viruses that have been hiding quietly in your body since childhood can wake up in space. Over half of astronauts on shuttle and ISS missions showed detectable levels of at least one reactivated virus during or after flight. Your brain also reorganizes itself. MRI scans taken of astronauts before and after long missions show measurable changes in brain structure. The brain physically shifts upward inside the skull due to the fluid redistribution. Gray matter volume changes. Areas responsible for motor control and spatial orientation actually remodel. Researchers at the University of Michigan, led by Dr. Rachel Sadler, published findings showing these structural changes can persist for months after returning to Earth. And your sleep collapses. The International Space Station orbits Earth roughly every 90 minutes. That means you see a sunrise and a sunset every 90 minutes. 16 sunrises per day. Your circadian rhythm, the internal clock that tells your body when to sleep and when to wake, is built for one sunrise every 24 hours. In space, it breaks down. Astronauts routinely report sleeping fewer than 6 hours per night. They rely on medication. Their cortisol patterns shift. Their alertness drops. Scott Kelly described feeling chronically tired during his mission, not just physically, mentally. His brain was running on a clock that the universe kept resetting every hour and a half. Now think about all of this together. Puffy face, thinning legs, growing taller and then shrinking back painfully. Losing bone, losing muscle, blurring vision. Radiation soaking into your DNA, telomeres behaving erratically, viruses waking up. Your brain physically reshaping itself. Your sleep destroyed by 16 daily sunrises. This is what 1 year does. And Scott Kelly had the best medical monitoring on Earth, watching every single data point. He had exercise equipment, controlled nutrition, communication with family, and a planned return date. Imagine doing this for 2 years. 3 years. The trip to Mars at current propulsion speeds would take roughly 7 to 9 months one way. With surface time and return, you are looking at 2 to 3 years of total mission duration. Your body would change in ways we have not yet measured, ways we might not be able to predict. And yet, when Scott Kelly was asked, after all of this, after the pain, the exhaustion, the radiation, the bone loss, the blurred vision, the shattered sleep, whether he would go back, he did not hesitate. He said yes, because something else happens to your body in space, something the studies measure in scans and blood panels but never fully capture. Your perspective shifts. You look down at Earth, this thin, fragile, blue-white sphere wrapped in a paper-thin atmosphere, and something in your brain recalibrates. Astronauts call it the overview effect. A sudden, visceral understanding that every war, every border, every argument you have ever had is happening on a tiny, wet rock hurtling through an incomprehensible void. Your body deteriorates in space. That is the cost. But your understanding of what it means to be human, of what Earth actually is, of how small and connected everything is, that changes too. The question is not whether space will break down your body. It will, that is certain. The question is what you are willing to lose in order to see things from the other side.